So today we are going to move into what we call open proof writing. So that is different from what we were doing last week where we were exploring closed proofs. Closed proofs look at actual, tangible, definitive shapes that have specific lengths, angle measures, coordinates, and you're asked to prove that that shape is the most specific name as possible. And you prove that by showing, hey, these two side lengths are identical and these degree measures are 90 degrees and so forth, trying to meet and show that the different elements that are in the definition of that shape actually apply. And they apply because you have definitive numbers. Both these side lengths are 5, both these angles are 90 degrees. You need to let students do that first so that they can see the idea of what it means to prove something, to show that equality actually holds. And there's a certain trajectory or stages of learning that you want to go through with your students in a math class to ensure that they can actually write proofs and truly understand them. So in our PowerPoint, we look at 3 math educational theorists. One is Zoltan Dinez. He's an internationally renowned Hungarian mathematician, educational psychologist who believes strongly in the concept of constructivity, the idea that students need concrete experiences prior to studying abstract concepts. So again, studying closed proofs before moving on to open ones. This is reiterated and reinforced by David Ausubel, who's an American educational psychologist who focused his research largely on the importance of meaningful math discourse. That means that not only do students need to work with tangible objects, they need to talk out loud and write concretely what they are seeing happening. They need to describe math concepts in their own words. If they can't articulate it, then it exists only in their mind, and it only exists to a certain level of understanding. It isn't rounded out and complete because they can't put it into words. And there's something about orating and saying what you think that actually makes it clear to you and clear to the audience that you're trying to describe it to, obviously. And then finally, Jerome Bruner, who's an American educational psychologist, who identified 3 phases of learning that also reinforce what Dinez and Ausubel said. Those 3 phases, which are in the PowerPoint, talk about an active representation. That's action-based. Students work with concrete materials to explore concepts and begin to develop meaning. This underpins a lot of Montessori learning and the use of manipulatives, which we explore quite a bit in EDU 331. Exploring with concrete objects is critical. The next phase is iconic representation. It's image-based. Pictures and diagrams are used to represent concepts being studied. That's much of what we did last week when we were dealing with concrete objects, but in a technological environment. So we were graphing them. So they weren't 3D, they were still concrete, but they were image-based on a screen. That's an important scaffold for students to the next phase, symbolic representation, which is language-based. Students are able to understand and use symbols and other abstract forms to represent concepts. You can't move immediately into this type of proof writing, which we're going to do today, without having students prove things for concrete images. Okay, so before we scaffold into the proof writing that's here, and I encourage you print the in-class problems dealing with congruence and similarity, because we'll be working on the sheets for that in these videos. In the next couple videos, we'll deal specifically with congruence because Thursday's lecture will be on similarity. But before we do that, I want you to engage in a little activity. The activity that I want you to engage in has you looking at what we call a quadrilateral hierarchy. Quadrilateral hierarchies are often used because they are image-based and they allow students to understand relationships that exist in a pictorial fashion between different quadrilaterals. Now, without me stating any of the relationships that exist, I want you to look at this and think to yourself about the following question. How does the above hierarchy help to clarify relationships among quadrilaterals and demonstrate how properties are inherited? Think about that and then share with somebody near you, or if you're in quarantine, share with yourself. So something important to think about with the quadrilateral hierarchy is the way that it's designed and the way that properties flow. If you're moving down, those properties that come from the prior object whose arrow is pointing at something, they're inherited. So a rhombus would inherit all of the qualities of a parallelogram, which would also inherit all the properties of a trapezoid. And you might say, what? I thought trapezoids have only one set of parallel sides. Some definitions will say that. They'll use the word only. That means it's an exclusive definition. A quadrilateral hierarchy, it would be an exclusive. A quadrilateral hierarchy is inclusive, meaning that instead of saying they only have one side of parallel sides, they have at least one. And you'll notice from the definitions handout that I gave to you in class on quadrilaterals, the definitions that we're looking at are all inclusive. They don't exclude different properties. So the definition we use for trapezoid was that it's a quadrilateral that has at least one set of parallel sides. If you say it has at least one set of parallel sides, then a parallelogram inherits those properties and in addition has a second set of parallel sides. So guess what? A parallelogram by our definition would be called a trapezoid, okay? So these properties flow down. Do they flow back up? No, not necessarily, right? They do not necessarily flow back up. Now, a square has all equal sides. A rhombus does too, so that property could go in this direction, but a rhombus does not need to have all right angles. So the properties flow down. What about when you travel right to left? Could a kite be a parallelogram? Could a parallelogram be an isosceles trapezoid? The answer there would be no, because a kite has two distinct congruent sides. A parallelogram does not need to have congruent adjacent sides. And in an isosceles trapezoid, your base angles both have to be congruent to each other. That's not the case for a parallelogram, is it? No, it's not. So the properties would not translate if you're moving horizontally. Use this diagram and take some time to respond to the questions below. You're responding sometimes, always, and never. Okay, hopefully you've paused this and filled this out. A rhombus is a square. That could be a sometimes condition. A rhombus could sometimes be a square if all of its angles were right angles. A square is a parallelogram. That's an always, because remember, all these properties flow down and a square inherits all the properties of a parallelogram. A parallelogram is a square. That again would be a sometimes. If all of your sides are equal and the angles were 90, then your square and your parallelogram could be a square. A parallelogram is a trapezoid. Is it a trapezoid? Yes, because it has at least one pair of parallel sides. So that would be an always statement. If it said a parallelogram is an isosceles trapezoid, that would be a never. A rhombus is a rectangle. Now, I would honestly accept two answers here. I would accept never, because I had just said these two things can't translate across, because a rectangle has all 90-degree angles, and a rhombus has all equal sides, and a rectangle does not have to have all equal sides. However, if a rhombus did have all 90-degree angles, which would in effect make it a square, then it would be a rectangle. So if a student rationalized it, I would take a sometimes there, but also a never. A quadrilateral is a rectangle. That is also a sometimes. Okay, this is video 1. We'll pick up on video 2.